All right. So thanks again, Walter, for the very fine introduction. I do very fondly remember our first interaction. And today I'll be talking to you about, broadly speaking, how we can use neural techniques for combinatorial optimization and apply them to reasoning on natural inputs. So what I'll be talking about today in this talk is largely the classical algorithms that you might encounter in a typical computer science curriculum. So things like sorting, pathfinding, dynamic programming, and so on. And then I will see how, just with a little bit of neural spice in the right place, you will be able to vastly expand the kinds of possibilities that you can have with these classical algorithms. So without further ado, I'm sure a lot of you already have this motivation in mind, but I felt like it's good to be exactly on the same page on what is it that makes algorithms such a great thing to study. So the reason why I like to study algorithms is because I think of them as essential pure forms of combinatorial reasoning. You can think of them as basically these timeless principles, and they will probably remain relevant regardless of what computation model you're using. Is it a CPU? Is it a GPU? Is it a quantum computer? You can probably expect algorithmic reasoning to be a very key component in any of these platforms. And reasoning about algorithms allows you to, for the most part, completely decouple from any form of perception and just focus on what is the thing that you want to combinatorially optimize. And beyond that, they just have many very favorable properties, like they trivially strongly generalize. They can be split up into various subroutines, which makes them compositional. And you can usually prove that they're correct and that they will have a certain time or memory complexity. And usually they're written in this pseudocode form, which allows you to interpret their operations very nicely. And at least for me, and I believe for several people in the audience here, it hits very close to home because algorithms and competitive programming are generally how I got into computer science in the first place, way before I discovered machine learning. So hopefully this gives a bit of a good starting point for why algorithms are a good idea. And I would like to really dig in and give you a concrete example of what I mean by all these nice properties. Specifically, I've been looking at the maximum flow problem, which should be familiar to many of you. Just real quick, we can specify an input to a flow problem using these flow networks, which are graphs that are augmented with a capacity function. And a capacity for every pair of nodes will tell you how much flow am I allowed to unleash along that edge. Two vertices in the graph are special. They're the source S and the sink T. Source can unleash infinite flow and sink receives infinite flow. And you can define a flow as any mapping from pairs of vertices to positive reals such that it satisfies a few constraints. Namely, on any pair of vertices, you cannot unleash more flow than there is capacity. And for every vertex which isn't one of these two special vertices, all the flow that comes in must equal all the flow that comes out. So flow is conserved along the flow network. And once you've defined a flow in this way, we're trying to find a flow which is in some sense optimal. And one particular quantity that's very relevant is what's the value of a flow. That's the total flow that emanates from the source. So all the flow unleashed from the source vertex minus the total sum of the flows going back into the source vertex. And we are typically interested in optimizing this, like unleashing as much flow as we can, because this can give us a good idea about the bottleneck properties of our flow network. So here is just one example of a flow network with marked S and T nodes. And for every edge in the graph, you have a clearly defined capacity, which is given on the right-hand side. And on the left-hand side, we've unleashed a certain number of units of flow. You can see that it's a valid flow for every vertex other than the source and the sink. The flow coming in equals the flow coming out. And at no point did we exceed the capacity of a particular edge. And in this particular case, we cannot unleash more than 17 units of flow. I'll get back to this example in a bit, but hopefully this gives you a nice visualization of what we're trying to solve here. Once you define a problem so rigorously and abstractly, it's very convenient because it allows us to come up with these elegant and often provably correct simple algorithm blueprints. And in this case, you know the famous method of Ford and Fulkerson, which starts with initializing the flow to 0. And then as long as I can find a path from the source to the sink which hasn't been fully filled up, a so-called augmenting path, I can augment as much as possible flow along this path until it's no longer possible, and I can return my flow. And depending on exactly how I find this augmenting path, I can recover many different specific instances of the Ford-Fulkerson blueprint, like the Edmonds-Karp algorithm or Dinitz's algorithm and so on. And no matter which one you choose, it can be easily proven that this will terminate with the correct solution. So let's just quickly see how this algorithm performs. Let's say I want to start by unleashing as much flow as possible, and this particular path unleashes 8 units of flow, which is the most I can unleash at this one particular point. Going further, I can find a different path which unleashes 6 units of flow, going down this path down and up. And then I can further saturate the top edge to capacity 10 by unleashing 2 more units of flow along the top path. And finally, we're not quite done, even though it seems there's no direct path, because any flow that we unleashed, we can also return if it's more meaningful. So in our final iteration, we'll unleash 1 more unit of flow on the lower path, but we'll actually return 1 unit from the previously fully saturated edge of capacity 8. And now, after we have done this, we have converged to an optimal solution for the max flow problem. So hopefully this gives you kind of an intuitive view of Ford-Fulkerson if you've never seen it before. I found it quite useful to visualize. Another thing that's quite useful when you look at data and problems in this abstract way is because you can very easily spot connections between things that maybe if you worked with raw data, it wouldn't be that easy to connect them together. And in particular, you can derive these very interesting theorems that can connect the problems very strongly. In particular, in this particular setting, you might be familiar with the max flow min cut theorem, which directly relates a maximum flow in a flow network to a minimum cut in that same network. Problems that appear to be roughly unrelated, but are solved by more or less the same algorithm because of this theorem. In particular, once you've saturated your flow network to the maximal point, you can cut off all of the saturated edges, and this will always define a cut of the graph that splits S from T, and there is no way to obtain a cut which is more efficient than that. In this case, the minimum cut is indeed 17 by cutting off the 2 bottleneck edges away from the source. So hopefully this very quick rundown through flow algorithms gives you a nice way of thinking about why is it good to study algorithms in this abstract way. Now, there is a core problem with this because, okay, we designed these classical algorithms with abstraction in mind. We force the inputs to conform to these stringent preconditions. And this is good. It allows us to keep focus on reasoning, discover interesting connections between problems, and usually very easily certify the correctness of what comes out of any algorithm we come up with. That means we can actually place stringent postconditions on whatever comes out. But we should never forget why we actually design algorithms in the first place. And unfortunately, these two desiderata are at timeless odds. So to kind of illustrate this, I will show to you how already in the 1950s, through the maximum flow problem introduction, by coincidence, it was shown that it's not always easy to do this abstractification so that we keep alignment with the real world. Namely, the original paper that introduced the max flow problem in the 1950s by Harris and Ross has studied it in the context of the US military, where both Harris and Ross were placed at the time. And they were looking at, in the context of the Cold War, at analyzing the Warsaw Pact railway network. I've left here the link to the full paper if you'd like to go through it. In my opinion, it's a very fun and elucidating read. So in the paper, they detailedly draw out the sketch of what their current belief is that the Soviet railway lines might look like, and they're interested in finding the bottleneck, which is basically related to the minimum cut. You might see it on this picture if you check out this line that starts from the Baltic Sea. And this basically gives you a set of edges that need to be interdicted in order to maximally dislodge the capacity of the railway network. As we saw, we can directly link this problem to computing the max flow, and intuitively, Harris and Ross have assumed this as well, even though in 1955, it was still not known that max flow and in-cut are related problems. And in one passage, which I quote verbatim from the paper, already in 1955, Harris and Ross have identified one key issue of trying to apply classical algorithms in the real world, and that is the fact that in order to pose the Warsaw Pact Railway network as a flow network, you need to compute a scalar capacity in every single edge of your graph. But the real world system, the railway network, is far more complicated than that. There's a lot of raw real world observations you might have, and based on them, you have to come up with this one scalar that summarizes the entire edge. And as they note very much duly so in this paper, this is seen to be very much an art. And no matter how intimately someone has been associated with the territory they're studying, the final capacities that you come up with, no matter how accurate it might seem, is one of judgment and experience. That means that it's prone to failure. So, in my opinion, this is a very important issue for the community as a whole because it plagues applications of combinatorial algorithms to this day. In order to satisfy their preconditions, you must convert your potentially raw and rich inputs into this abstract, tiny form. And if you do this manually, like many people are still doing today, it often implies drastic information loss. Your combinatorial problem basically no longer accurately portrays the dynamics of the real world. So even though your algorithm will give a perfect solution, it will give a perfect solution in a totally useless environment. So the results of the algorithm won't really be that useful for making actionable decisions. And actually, even more brutally than that, the data that you might need to make the algorithm applicable, and I will consider this again later during the talk, it may actually only be partially observable. And this would make the algorithm in most cases completely inapplicable. So this issue of abstractification versus the purpose of the design of the algorithm in the real world is something that's of high interest for both combinatorial research and operations research communities. So I hope that some of the solutions I present today might be of interest to everyone here. So I mentioned at the beginning, we wouldn't just be talking about classical algorithms. We would also see how we might neurally spice them to arrive at interesting solutions. And I'll just quickly recap what we have so far. We might have some real world inputs, for example, this real world state of a traffic network, cars moving around, creating traffic jams at various points, traffic lights, which also non-trivially change the dynamics. You could have unpredictable weather conditions or roadblocks or something like that. And we're interested in finding the shortest path from A to B, for example, in this road network. This would, in the algorithmic sense, require somehow converting the problem into an abstract road network representation that you can then apply an algorithm like Dijkstra's to, which would compute you this shortest path tree highlighted in red edges. So what we're doing is we're starting from natural inputs. We want to somehow cast them into these abstract inputs that are refused to a combinatorial algorithm. And then applying the combinatorial algorithm, we can compute abstract outputs. Now, the step from natural to abstract inputs is often either done by humans or by human designed heuristics. So this should be something that's familiar to those of you who have done a lot of deep learning. Whenever you see manual feature engineering of huge quantities of raw data, this is usually the case, like from previous years. We've seen that when we appropriately apply neural nets in this setting, we can recover huge wins. So let's try to do that. Let's try to do quote unquote good old deep learning and just replace the human feature extractor with a neural network. So now a neural network is responsible for computing the inputs to the algorithm. We still apply the same algorithm. Well, there are two key issues with this. So it's not as simple as, say, replacing feature extraction with convnets in ImageNet. The first issue is that algorithms typically perform discrete optimization, which means that neural nets, which require nice gradient-based results from whatever their data is piped into, they won't get such nice gradients necessarily if their outputs are piped through an algorithm. So this is the first issue. And I would actually like to say that we have a very good set of solutions for this problem already. Marin Vlastelica and others have presented this awesome paper at iClear, which gives a great approach for differentiating the outputs of any black box combinatorial solver. So this is great. And it gives some really interesting results. Like you can take these Warcraft maps at the bottom left corner here, and their method is able to meaningfully extract a distance matrix for applying an algorithm like Dijkstra or A*, and it's actually able to find the shortest path within this super, high-dimensional pixel-based input. So, in a way, like there's already quite exciting research going on in this direction of allowing neural nets to play nicely just with fixed black box combinatorial algorithms. But there is a more fundamental issue that I see here, and that is an issue of data efficiency. So even if we get good at pushing gradients out of a combinatorial optimizer, real-world data is often super rich, and most of these algorithms still require just scalar values. So you need to compress the richness of your real-world data into just one scalar value per edge or something like this. And the algorithmic solver then commits to using the scalar and assumes that you've computed it perfectly. Now, from a neural network's perspective, this is a bottleneck. So if you don't have enough training data to properly estimate these scalars, you've hit the same issues as before. Your algorithm will give a perfect solution, but it will be a perfect solution in a suboptimal environment that doesn't perfectly model the kind of problem that you're facing. So we would like to ideally break this bottleneck, and the way in which we can attack it is by noting the fact that neural nets derive great flexibility from having a latent representation, which is usually high dimensional. So if any component of a high dimensional latent ends up being poorly predicted, other components can step in and compensate. So what we will do is we will replace the combinatorial algorithm that we had before with a neural network executor. So it gives us this natural encode, process, decode pipeline, where now inputs are not mapped to abstract inputs, they're mapped to a latent space of a high dimensional vector. And there's a processor network that goes from latent state to latent state, simulating one step of the algorithm that we care about. And then at any point, we can take the latent state and decode solutions whenever we think that, that this is appropriate to do. Now, assuming that we have a processor network that aligns really well with the steps of the algorithm, what we've just built is an end-to-end neural pipeline, which is fully differentiable, and there's no scalar bottlenecks, so we will have higher data efficiency. So this seems to be a great solution for the problem that we have. Now, the big problem is, how do we actually obtain these neural networks that are purely in the latent state and will align nicely with a combinatorial algorithm so that we don't actually have to apply it? And this brings us to algorithmic reasoning, which is a recently emerging area of research that I've been lucky to contribute to on a few occasions. So one key thing to notice here is that what we want out of this neural network P is slightly different than usual, like the usual kinds of things we ask neural nets to do. Neural nets are usually asked to interpolate a training data set and like predict good outcomes for something that's expected to be similar to the training inputs. But here you want to imitate steps of an algorithm very faithfully, and that means by design you should extrapolate. So you should be able to have your neural net algorithm executor applicable even if I give you an input that's twice as big with wildly different input ranges or something like that. And neural nets are known to really struggle in this extrapolation regime. So what algorithmic reasoning is all about is it's just an emerging area that tries to make this issue a bit better. And it does so through a combination of theoretical and empirical prescriptions. So what kinds of neural architectures you should use, what kinds of inductive biases you should use, and what kinds of input features you should feed to the neural net so that you're a little bit better at combinatorially extrapolating. Now, this is a super active research area, and there's many key papers published only in 2020, so there's a lot of stuff to unwind there. And for the purposes of this talk, I just really wanted to give you a TLDR, so a very quick run through of some most interesting papers that you might want to look at. We know, for example, that it's probably a good idea to use a graph neural network to serve as the processor, because they're known to align well with dynamic programming, and most polynomial time heuristics are expressible using the language of dynamic programming. But just throwing a GNN at a problem is not enough. It's not going to extrapolate well. It's just going to learn the hacks of the particular abstract input-output data you feed it. So in our paper at ICLR 2020, we investigated some interesting inductive biases to add to a GNN. And in particular, we found it very useful to do encode, process, decode from abstract inputs to abstract outputs. We found it very useful to use a max aggregation, which, as you can see on the figure on the right, aligns really well with most dynamic programming update rules, pathfinding algorithms, and so on. And further, we found that it's very useful to do strong supervision on various trajectories. So we don't just care going from abstract input to abstract output. At every step of the processor's execution, we want to be able to decode meaningful stuff out of the processor's representation. For example, in the case of shortest path finding, after k steps of a processor, we should be expected to find shortest paths that use no more than k steps away from your source vertex. There's a lot more interesting work that came since then that proposes even more exciting inductive biases. I've just listed 3 here, iter-GNNs, shuffle exchange nets, and pointer graph nets, which also incorporate data structures into the whole mix. And some latest insights, a paper that's just been published at IPAM 2021, is that if you design the different parts of your network and your input features such that you learn functions that are as close to linear as possible, this will be highly beneficial to your extrapolation performance. This is a super nice paper. I would highly recommend checking it out. But unfortunately, I don't really have the time within this talk to go in detail about how to design these inductive biases. I actually have 2 previous talks dedicated entirely to neural algorithmic reasoning and how we can construct meaningful neural networks to reason like an algorithm. So I would highly recommend checking out these 2. I will share the slides afterwards, so you'll be able to access them, but they are both available to view straight away. So overall, what does this blueprint that I just presented give us? What we do first is we learn an algorithmic reasoner from abstract inputs to abstract outputs. So here, for example, breadth first search, we have inputs where source vertex is tagged and everything else is at infinity. Now we learn an encoder that maps that to a latent space, a processor network which simulates the effects of, say, breadth first search in this latent space, and finally a decoder network that goes from there to abstractified outputs. So, for example, these shortest path trees. Now, once I've trained the model in this way, I can actually take my P network, which is now guaranteed to be a good algorithmic reasoner that aligns with BFS, and I will freeze its parameters so that now I can attach that as a differentiable component for something that takes in natural inputs and has its own encoder and a decoder to produce natural outputs. So if I know that my problem will require some kind of breadth first reasoning, I can just take this pre-trained model and use it as part of a fully differentiable end-to-end algorithmic reasoning pipeline. And in my opinion, this is like one of the key potentials of this blueprint. Finally, I would like to show you, yes?
Okay, so I didn't know if you heard me just a minute ago, but you have 5 minutes left. So.
Yeah, sounds good. Thank you. So finally, I would like to present how we can use this algorithmic reasoning blueprint and how we already used it to come up with a novel implicit planner in the space of reinforcement learning. So for those of you who are not familiar with reinforcement learning, I tried to summarize it here in just one slide. You have an agent pictured by this robot here that has a particular state, and what it wants to learn is a policy that, based on the state, selects actions to perform in an environment. And then the environment responds to the agent by giving it a reward for this action and a new state that the action should assume. And the whole system is governed by this transition and reward model, which are basically probability distributions of the next state and the observed reward based on the current state and the action that you've performed. And the objective of the agent is to maximize, to pick a policy that will maximize these rewards while not necessarily knowing P and R, so not knowing the dynamics of the environment. It's a very generic setting. It's applicable in a broad range of circumstances, and therefore it's very nice to study it also from this lens. And within this space, value iteration is a very famous dynamic programming algorithm that can perfectly solve the environment using this iterative rule. It's actually guaranteed to converge to an optimal solution, the fixed point of the Bellman equation, this V star, where V star will give you the optimal value in every one of your states, and you can use that to help you select actions. The problem with value iteration is that it requires full knowledge of the underlying system you're simulating in. So you need to know the probabilities of transitioning, and you need to know the rewards upfront. And because you don't have that knowledge, value iteration is usually not applicable in most real-world reinforcement learning settings. However, this makes it a prime target for our previously studied algorithmic blueprint. So in the Excelvin paper, which was led by Andrea Deac and myself, we showed how our algorithmic reasoning blueprint can apply in this setting. So we have a particular state, like the frame of an Atari game here on the left. We apply an encoder function to reduce it to an embedding. And then by learning some self-supervised transition model, we can actually build a local graph around that particular state. This represents the outcomes of performing the individual actions in this tree-style structure. And once we have built this local graph, we can execute a pre-trained graph neural network that was taught to execute this value iteration algorithm using the blueprint I gave before. And those updated embeddings that are now also mindful of the neighboring state embeddings are used to predict whatever you need in this environment, like policies or values. And what we've actually found is that this method in some standard high-dimensional RL environments like Atari is quite beneficial for learning in super low data environments. So here we have plots for the first 1,000,000 transitions observed in the environment. On the first line, we compare our method against a standard baseline, which doesn't use this graph-based algorithm execution thing. You can see there's a clear advantage to the baseline in most cases, especially in low data. But what's particularly interesting to me is the lower line of plots, where we compare our method against this A3C, not to be confused with A3C, A3C method, which actually does the same thing as we do for building the graph, but then they predict the scalar in every state, which is like the value, and then they explicitly apply the Bellman iteration. So this is like the comparison against this method is basically what I said before about the scalar bottleneck. Can we avoid the scalar bottleneck by using high-dimensional latent algorithmic executors? And hopefully you can see in the plots here, when you've observed enough data, 600,000, 800,000 iterations, the method that predicts scalar bottlenecks usually catches up to our method. But in the lower data regime, which is also quite important for some RL setups, our method is almost always clearly on top of the A3C method. So hopefully this gives you another kind of data point for why this is a good comparison. And if you want to know more about this, there's obviously a lot more details that I did not have the time to cover here. We've recently put out a 43-page survey on graph neural nets for combinatorial optimization. And in particular, section 3.3 details this algorithmic reasoning blueprint and some comprehensive references in the area. If you're interested in neural nets, especially graph nets for combinatorial tasks, I would highly recommend to check out parts of this paper. On that note, I would like to thank you very much for listening. I'd be very happy to take any questions you might have. And generally, you can also contact me offline via email, or all of my social networks are listed in the web link below. And I'd like to thank all of my collaborators on the various works presented here. They are now too many to enumerate directly. So thank you to each and every one of you. And yeah, I hope you enjoyed my talk, and we'll be really happy to hear the questions you have.